All right. So in the last lecture, or in the last few lectures, we have been looking at how one can step down or convert a given DC voltage level to a different smaller voltage level. And based on the idea of using switches to obtain a pulsating DC waveform, followed by filtering that waveform to get a steady DC voltage, we could then derive the circuit for the so-called buck converter, which then looked something like this. It had an input voltage source Vg, and then you had a switch which would connect this to some terminal where you will get the pulsating DC voltage, and then you connected an LC filter to filter this DC voltage, okay. And then you could connect your load, which would be typically a resistive load, across the capacitor and get the output voltage V0 across this load resistance R with a capacitor C and an inductor L. Now, since we are using an LC filter, we also required a path for the current to flow when the switch was turned off. So in order to do this, we then used another switch, right? And based on the characteristics of this switch, we said that we could simply use a diode instead of this particular switch. So this was the configuration of the buck converter that we obtained, and we can then label these switches as A and B. And then, using the principle of inductor volt seconds and capacitor ampere second balance, we could analyze the behavior of this converter at steady state conditions for both the continuous conduction mode, where the current through the inductor would be a continuous waveform, and the discontinuous conduction mode, where the current through the inductor would occasionally go to zero in every switching cycle. Okay. So in this so-called CCM, we have found that the buck converter gives you a voltage gain VO by Vg, which was equal to the duty ratio at which the converter was operating. And in the discontinuous conduction mode, then you had a voltage gain which was given as D divided by D plus D2. So we have already seen what D and D2 means with reference to the inductor current waveforms. So then we also looked at sort of the boundary between this CCM operation and DCM operation. So that is the case where the current just touches zero, and we analyzed this particular operating mode to figure out what is the point or the region where the converter operation switches from CCM to DCM, right? And so based on this analysis, we could then define a critical conduction parameter K, which was defined as 2 times L divided by RTS, and this parameter would then indicate the tendency of this converter to operate in either DCM or CCM. Okay. So having seen all that, now let us proceed to look at an example design for such a converter starting from certain specifications. So we are looking to design a buck converter to meet certain output voltage and ripple specifications. So let us look at the specifications, which we will take it as given. So we need a output voltage V0 of 108 volts. Okay, so you may refer to the battery electric vehicle situation where we saw that we require this type of an output voltage to charge the battery, and the input voltage was then obtained by rectifying some AC supply, so it will have variations. So let's say that the input voltage varies between 300 volts to 340 volts, and let us choose the switching frequency that is specified for this application to be something like 25 kilohertz, and we want the output peak to peak voltage ripple to be limited to 1 volts. Okay, so that means the output voltage should have an average value of 108 volts, and the peak to peak value should be having 1 volt difference, and we will design this converter for a fixed output current I0 is equal to 6 amperes. And so again, it may so happen that your output current is not always at a fixed value, it may also vary, but for the sake of illustrating the principles of this design, let us go for a simplified version where the output current we will assume it to be a constant value. So first of all, to begin the design, we need to decide upon what is the operating mode of this converter. So let us assume a CCM operating mode, okay, and design this converter. So as we have seen in CCM operating mode, the duty ratio is given by the ratio of output to input voltages. So here we have a case where the output voltage is fixed while the input voltage seems to be varying between some range. So accordingly, when you operate the converter, you will find that the converter duty ratio will also have to be varied in order to maintain the output voltage. So you will have a minimum value of duty ratio D minimum, which you can calculate it as 108 by the maximum value of input voltage, right? This will give you the minimum value of duty ratio, and if you evaluate it, you will get 0.3176. Similarly, to get the maximum value of duty ratio D max, you will then have to look at the minimum input voltage. So this D max is given by 108 divided by 300, which would be 0.36. Now to proceed further with the design, we need to choose a value of the ripple current that is going to flow through the inductor, because we know that the output current is 6 amperes, but to choose the switch as well as the design of inductor, we need to figure out what is the maximum value of current or the peak current that is expected to flow in this converter. So for that, we need to choose the value of delta IL, or rather the maximum value of delta IL, we need to choose it, and in this case we may choose a value of something like 2 amperes. You could even choose a different value, you could even choose it as 1 amperes, okay, that's a design choice, but since you have assumed CCM operation, okay, you should make sure that the current ripple is not so high as to make the converter go into DCM, right? So this is something which you have to take care while designing or while choosing the delta IL max. So anyhow, after having chosen the delta IL, right, we have already seen what is the expression for delta IL. So delta IL is given as the slope of the rising current, which is Vg minus Vo divided by L, times the duration for which the inductor current rises. So it is Vg minus Vo divided by L times dTs. right? So from this equation, now you have to find out what is the maximum value of delta L, okay, and at what value of Vg or D this maximum value appears, we need to figure it out. But from the equation, we have two terms which are varying, Vg also varies and D also varies. So it is not very clear at what point of D or Vg we are going to have the maximum value of this delta L. So we need to recast this in a different form where it becomes more clear as to what is the value of D at which we have maximum delta L, right? So we can do this by using the relation VO by Vg, which is D. So if you substitute this over here, Vg is then VO by D, so you have VO by D minus VO divided by L times dTs. And so D comes in the denominator, it gets cancelled. So you have VO times 1 minus D divided by L times Ts. So from this expression, now it is clear that delta IL will be maximum at what value of D? It will be maximum at the minimum value of D, right? So this value is D minimum and then Ts. Right, so now we have all the necessary information. We have delta L max is 2 and this should be equal to VO is a constant 108 times 1 minus D minimum, which is 1 minus 0.3176 divided by L times Ts from the numerator can be brought to the denominator and it becomes the switching frequency Fs, which is 25 kilohertz. So therefore, now you can calculate L directly from this. L goes here and 2 comes here, and so if you evaluate this, you will get the value of this L as 1.474 millihenry. Okay. So having defined the value of L, now we have to look at what is the value of C that will restrict the voltage ripple to the specified value of 1 volt peak to peak. Okay, so let us look at the capacitor current waveform then. So we have already seen how the capacitor current waveform is going to be like. Right, so this is ICT, and if you look at this waveform, it would be something like this. So let me draw it. So it would be going in this fashion. Right? And this particular time period would then be half the switching frequency. So we could draw this waveform directly because we know that the average current through the capacitor should always be 0 at steady state, and therefore whatever ripple component that is present in the inductor current is the only one that is going to flow into the capacitor. Right, so we could also now label this peak value. This is delta IL by 2. And what would be the charge that goes into the capacitor, which will result in the ripple component, is then basically given by the area that is enclosed either in the positive half or the negative half. Right, both are equal, and therefore you could calculate one of these areas and it will give you the total charge that goes into the capacitor during the variation of its voltage, right? So this charge, if I call it as delta Q, is nothing but the area under this positive portion or the negative portion, and that should be equal to C times delta V peak to peak, right? And so this area is given by half into Ts by 2, which is the base, and then you have delta IL by 2, which is the height of the triangle. So delta V peak to peak is 1, so directly you will get the value of C from here as delta IL, and if you bring Ts to the denominator, it becomes Fs, so this becomes delta IL by 8 Fs, or so Fs is 25 kilohertz. So if you do this calculation, you will get delta IL is 2 amps divided by 8 times 25 kilohertz. So this you will get it as 10 microfarad. Okay. So that sort of completes the design for this converter operating in CCM. You have calculated the L values and C values. So what remains next is then that you could either go and build the converter hardware and look at how it performs, or a wiser step in this situation would be to actually use a simulation software to simulate the behavior of this converter and verify that everything is working as per specifications before you proceed to go and build a hardware, right? So there are several simulation softwares available where you can do these type of activities. So one is, you can use the MATLAB Simulink environment. Okay, there you can build this type of converters and then verify the performance. Or another such software is PLECS, which is also specifically designed to work with these type of power electronic circuits. It's a more specific software compared to MATLAB, and it will be recommended for this course. We have obtained the licenses, so you will be able to simulate using this. And another software that may be useful here is LT-Spice, which will also help you to run these type of simulations. But LT-Spice will be particularly useful at a later point when we start looking at switching devices and their characteristics during the switching transitions. Okay. So as I said, it would be a good option to simulate these waveforms, and I have done this for this particular design. So let me show you some of the waveforms. Okay, so I can insert this. Okay. So here is the waveform of the converter, which is obtained by operating under continuous conduction mode. Okay, so let me make it a bit smaller. Okay. So what you see in the top, this green waveform, is the voltage across the capacitor, and this red waveform is the inductor current. Okay, this blue one is the capacitor current, and this bottom waveform is the current flowing through the semiconductor switch, or it is the same as also the current coming out from the source voltage of the buck converter. So clearly you can see that as per our design, we have said that the output voltage ripple should be limited to 1 volt peak to peak, which seems to be the case here. It varies between 108.4 volts and 107.4 volts, and the average of this looks to be around 108 volts. Similarly, if you look at the inductor current, you can see that the inductor current goes from 5 amps to 7 amps. So that corresponds to our chosen value of current ripple, which was 2 amperes. Okay, and you can see that the capacitor current goes from -1 to 1 volts. So that corresponds to the value of the same voltage, same current ripple that is there in the inductor current. So this minus the average value of I naught, that is 6 amperes, is giving you this capacitor current ripple. And then the source current, if you look at it, you can see that since the transistor conducts only during the portion of rising inductor current, so you will see that current suddenly jumps to the minimum value of the inductor current, 5 amps, and then goes up to 7 amps and then drops to 0. So this is the portion where the diode is going to be conducting, and therefore the current or the inductor current actually flows through the diode, and none of this current flows through the source. And what I want you to look at is the waveform of the voltage ripple. So let me draw the reference point for this capacitor. So this is the 0 of the capacitor voltage. Okay, so if I draw another line which is sort of if I draw a perpendicular from here, so this line, and then if I draw a perpendicular from here, it would be that line, right? So this is the 0 crossing point. Okay, so what I want you to appreciate is that this point, which is the 0 crossing of the capacitor, to the next 0 crossing. So this is the point where the capacitor current, this is the region where the capacitor current is going to be positive, and you can see that the capacitor voltage, as per our calculations, is completely having a rising value. The slope is always positive during this portion. And similarly, if you look at the negative portion, right, you will see that the slope is always negative during the negative portion of the capacitor current. So that is the assumption that we have also made in calculating the capacitor voltage ripple. So it looks like our design is performing well. So we can go ahead and build this converter. And before going ahead with the next topics, let us also look at how one can design this converter in the CCM we have done. Let us look at how one can design this converter in the DCM mode of operation. So what we are looking at now is the DCM operation, and in the DCM mode we have the relation VO by VG is equal to d divided by d plus d2. We have seen that. And so again, similar to the previous case, to proceed with the design, we need to choose a value for the inductor current ripple, delta IL max. So in this case, what would be a good choice for delta IL max? So we can choose this value to be 20 amps. So this choice, as we have seen, the condition for DCM operation is that you should have a delta IL which is greater than 2 times the average current, right? Only under this condition you can say that the converter will be operating in discontinuous conduction mode. So we have here delta IL which is 20 amps, which is much greater than 2 times I0, which would be 12 amps. Okay, so having made this selection, let us see what we can do to calculate the L and C values. So as before, delta IL is given by the slope Vg minus Vo by L during the on time multiplied by the on time, which is dTs. Okay, so again here we have both Vg and D coming into the picture, and therefore it is not very clear at what value of Vg we are going to have the maximum value of delta IL. Okay, so we need to put this equation or recast this equation into a form which is convenient, which will tell us what is the value of Vg at which we are going to have maximum inductor current, right? So let us see how we can do this. So from the voltage gain equation, I can now write D is equal to Vo by Vg times D plus D2. Okay, so let me call this as equation 1 and this as equation 2. Okay, so if I substitute for D from this equation 2 into equation 1, what do I get? So right now I don't know what is the value of Vg which will give maximum, so I will omit the maximum. So if I substitute for the value of D into the equation 1, what I get is delta IL is equal to Vg minus Vo by L times dTs. So D is Vo by Vg times D plus D2 into Ts. So that is what we get as delta IL. We still have Vg as well as D in the equation, so we need to somehow look at how to eliminate D plus D2. So for this, again we can look at the situation of the inductor current when it is operating in the DCM mode. So if I plot the inductor current, right, as a function of time, then I will have a rising portion during the on time, and then during the off time it quickly falls to 0 and then remains at 0, and then the cycle continues. So this is how the waveform of inductor current would look like during the discontinuous conduction mode of operation. But nevertheless, whether it is CCM or DCM, the average value of this inductor current should always be equal to I0. We have seen that. So therefore, if I look at the average value, then this might be probably my average value of current, which is I0. Okay. And so if I write an expression for I0, right, I0 is the average value of this waveform, which is simply the area under the triangle divided by the time period. So you will get 1 by Ts times, what is this interval? This interval is nothing but d plus d2 times Ts. So it is 1 by Ts times half into d plus d2 Ts into, what is this height? This height is what we call as delta IL now. So that is delta I. Right, so Ts cancels out, and so we obtain the relation d plus d2 is equal to twice I naught divided by delta IA. So this we can call it as the equation number 3. Okay. So why are we doing all this exercise? Because we want to eliminate either Vg or d from these equations and make it into a form having only one variable, so that we will know at what value of the variable we are going to have maximum inductor current. So since we have d plus d2 here, it is convenient to eliminate it using the average value. Okay. So if I put the expression d plus d2 from 3 into this equation, so let me call this as equation 3, and this one let it be equation 4. So if I substitute for d plus d2 from 4 into 3, what does that give me? Delta IL is equal to, so it is Vg minus VO by L into VO by Vg, Vg minus VO by L into VO by Vg into, we have a d plus d2 times Ts here, so d plus d2 is 2I0 by delta IL, and then Ts, if I can bring it into the denominator, it would be Fs, right? So now we have only the varying term, which is Vg on the right hand side. All other terms are fixed, so we may use this expression to evaluate the value of L, right? So we can bring L to the denominator, so L to the numerator. So this will then give us L is equal to, or let us look at what is the value of delta IL max. So I take delta IL from the denominator to the numerator. So delta IL max would then be equal to Vg minus VO. So let me bring Vg here, multiplied by VO by L into 2I0 by Fs, if I bring delta L to this side. So this equation now contains delta IL in terms of Vg alone. So clearly we can now identify what is the value of this Vg at which delta IL will become maximum. So that is clear from this expression. If I put it in this term, 1 minus VO by Vg times VO by L into 2I0 by Fs. So clearly delta IL will be maximum when this particular value of Vg would be maximum, because Vg is maximum implies that VO by Vg is going to be minimum, and therefore 1 minus VO by Vg is going to be maximum. So this is the maximum value of Vg that is appearing in these equations. So then now I can substitute for delta IL and all other quantities to calculate L. So delta IL max square is 400, square of 20 is equal to 340 is the maximum value of Vg minus 108 divided by 340 times 108 by L into 2I0 is 12 divided by Fs is 25,000 Hertz. So now you can solve for L from this equation, and if you do that, you get a value of 88.46 microhenry. So now you see the effect of going into the DCM mode of operation, right? Previously we had a value of something around 1.47 millihenry, and that has now come down to 88.46 microhenries, which is at least one order of magnitude below the value of L in CCM. Okay, so having calculated this value of L, we now have to look at what is the value of C. For that, as usual, we turn our attention to the capacitor current. So the capacitor current would simply be a shifted version of this delta IL. So it will shift downwards by the amount of I0. So what you will then have for this capacitor current waveform is, it would be something like this. And then it repeats itself, right? So this is the waveform of ICT, and as usual, if we look at the area that is enclosed either below the positive half, that is this area, or one could also look at this area, which is the area under the negative half. These two areas are definitely going to be equal because the waveform has no average value. Okay, so let us look at how we can calculate this area. So we will denote this by T1 and this interval as T2, right? And we don't know T1 and T2, so we have to look at some way to find it out. But what we know is this value. What is this value? This is delta IL minus I0, because we have said that this waveform is just a shifted version. It gets shifted by I0. So this is delta IL minus I0. And we also know what is the slope of this portion, right? What is the slope of this portion? That is Vg minus Vo by L. And what is the slope of this portion? That also is known to us. It is simply Vo by L. So using this information, we can now calculate the magnitude of T1. So if you look at the magnitude, the height of this triangle, we can say it is delta IL minus I0, which is 14 amps. And that should be equal to the slope multiplied by T1. So it is Vg minus V0 by L multiplied by T1. And you know Vg, V0, L as well as the delta IL minus I0. So you can calculate T1, and if you do this, you will get T1 as 5.33 microseconds. And similarly, you can look at the other portion and try to calculate its slope. So again, you can write the relation as 14, which is delta IL minus I0, should be equal to the slope V0 by L times T2, and if you evaluate this for the value of L that we have calculated, you are going to get a value of T2 is equal to 11.46 microseconds. And so now you can calculate the area under the positive portion, which is delta Q, which is also equal to C delta V peak to peak. That procedure proceeds in the similar fashion as we did for CCM. So this is equal to half into T1 plus T2 into 14, which is delta L minus I naught. Delta V peak to peak is 1 volt, so C is simply equal to this value, and if you evaluate it, you will get it as 117.57 microfarad. So now you see that for the same design, even though the L value has come down, in the DCM mode of operation, you find that the C value has gone up again by another order of magnitude. It was 10 microfarad in the CCM. Now we find that C required is 117.57 microfarad. So that means now the design is done. So what is the next step is that we can go and try to simulate this. But again, for simulating this converter in the DCM mode, you have to have an idea of the duty ratio, which we still don't know. Okay, but then we know the relation D plus D2. We have seen that D plus D2 is 2I0 by delta IL, so you can calculate that. 2I0 is 12 divided by delta L is 20, so you have D plus D2 of 0.6. But again, that does not give you the value of D, so you can go and use this next equation, which says that D is equal to VO by VG into D plus D2. So D is equal to VO by VG into D plus D2, which is 0.6, and this value comes out to be 0.1905. So this is the duty ratio that you have to give to the converter for operation with this value of L and C, and then you may expect the output to be more or less as we have designed, and that should meet the specifications that is given. So again, I have done this simulation for the discontinuous conduction mode as well. So let us look at some of the results. So so that is the waveform that we get when we try to look at the operation of this converter in DCM. So again, you can see that this peak value is 20 amperes as per our design, right? And then you can see the capacitor voltage going from 107.6 to 108.6. So that is also as per our design, it is 1 volt peak to peak. And again, you can look at the capacitor current. So if I may draw the zero crossing, this is the portion where the capacitor current crosses zero, and therefore if I now draw a perpendicular from this point, you find that perpendicular meets exactly at the peak values of the capacitor voltage. So during this entire positive portion, of this capacitor current, this area, we have a positive slope for the capacitor voltage, and that is the basic idea with which we have designed also, right? So everything is fine, except that now you can see that your source current is a very peaky waveform. Okay, so you see that it goes from 0 to 20 amperes and it only appears for a very short duration. So this current actually appears for the duration of D, right? And so we have already calculated what that D is. So this duration is just 0.1905 times Ts. Right? So you see that there is a very peaky current which appears only for a very short duration, right? And then that results in a very large value of peak current in the device or through the source, whereas the average value of this component, so you can calculate what is the average value of Ig by assuming a 100% efficient converter. Ig is going to be V0 I0 by Vg, right? So this will give you 108 into 6 divided by 340. So this is something like 1.9 amperes you will get it for the average current, right? So what this means is that there is a lot of harmonic components apart from the average current of 1.9 amperes. There is a lot of harmonic components that are going to flow through this source, this voltage source, right? And these harmonic components, being at higher frequencies, do not really contribute to the power generated from the source, because your source is a DC voltage, right? And the power instantaneous, if you look at the time variation of power, it is going to be V times I, and if your V is a constant, then it is simply the variation in the current that appears in the power as well. So if you take an average over one switching period or one fundamental period of any of these harmonic components, you will find that the average power contributed by the harmonics is going to be 0. So these harmonics then just flow in and out of the source without contributing to active power production, but nevertheless what they do is they will heat up the source. Whatever internal resistance is there in the source, it gets heated up. So these are really unnecessary components, and therefore that is one of the main problems with DCM as well. Even in CCM we have this type of waveform where we have the current flowing only for some time, and therefore if you look at the average component in this case is also going to be equal to 1.9 amperes. That does not depend on CCM or DCM. But you will have a smaller harmonic component when you are operating in CCM, because you can see the peak current goes up to 7 amps only, and also the conduction is for a longer duration. You have conduction happening for 0.3176 times Ts instead of 0.1905. So here the harmonic component is going to be lesser in any case. So having done all this design, we may now go and build our hardware. You will select the components of L, C and so on, the switch, and then you will build this hardware and you will operate. Suppose that you are going to operate it at this constant value of D that you have calculated, similar to what you have done in the simulation. In this case, to your surprise, you will find that the results from the simulation are not exactly like what you get when you build the hardware and operate it with a constant duty ratio. So what has gone wrong here is that in all our calculations or in our designs, we considered all the components to be ideal, right? But that is usually never the case. If you take a source voltage, right? If you take a source voltage Vg, it is always going to have a internal resistance, which may be small rg, and any source that you take will always have this resistance. You can't do much about this. But this ideal deviation from ideal characteristics we have not considered in our designs. Similarly, if you take an inductor is nothing but a coil of wire wound around some core, and any coil will have a resistance. So whenever you take an inductor, no inductor is a pure inductor, you will always have a series resistance associated with this, we can call it as Ri, right? Again, if you look at the capacitor, you will find that the capacitor comes with another set of series resistance, and it will also have a series inductance. So this is your capacitor, and this resistance is what is usually called as the ESR, or the equivalent series resistance, and this is what is called as the ESL. And in these applications, it is mainly the ESR which is going to affect the performance more than the ESL. Why is that so? That is simply because in these converters you are designing the capacitors to carry a DC voltage, a steady DC voltage, and therefore it is mostly the inductance which will not affect the operation, rather it is the resistance which will cause heating in the capacitor, and if the heating goes and exceed limits, this capacitor is simply going to explode, right? So you should take care. So one way to minimize this is you can minimize the ESR, but that is not really in your hands. When you take a capacitor, you always have this ESR, there you have it, you cannot do much about this. So the other way is to simply reduce the harmonic ripple current through this capacitor, right? So for that, operating in the CCM mode will help you, and we have already looked at what are the advantages and disadvantages of the CCM and the DCM, and when one will choose to operate in DCM over CCM or CCM over DCM. So all those considerations apply equally well in this case also. Another non-ideality what you have not considered is that of the switch, which you have taken it like this, right? But no switch is such an ideal switch. At best you have something like a voltage source in series with an ideal switch, and in many cases you will also have a resistance associated with this. If you want a higher level of refinement, you will have to go with this model for the switch, right? So all this is just to tell you that what we have done is a very preliminary step towards the design. Okay, it is not the final thing. So we always have a closed loop control for these type of converters, so that even if there is a small deviation from the desired output voltage because of these type of non-idealities, the closed loop control will usually adjust its duty ratio accordingly, and you will have the value of output as desired, right? But where these non-idealities affects you more is when you calculate the efficiency of the converter. So the losses that happen in all these resistors and the drops across these series voltage sources, they will all affect the efficiency of the converter, and therefore when you design the converter for a given efficiency as well, then you will have to give more considerations to these type of parasitic effects. So the efficiency is more affected than the output voltage gain, we can say, because we anyway have a closed loop control to operate the converter, right? So that more or less completes our approach to design. So we will look at the next converter, that is the step up converter or the boost converter, in the next class. Okay, thank you.